All right. So last time we talked about vibrations in solids and how we could reconcile some of the experimental observations that were in clear contradiction with classical theory, how we could reconcile them by letting in a little bit of quantum mechanics into our description of solids, right? So we looked at Einstein's theory and we looked at Debay's theory, both quantum theories, and both gave us some improved match between what we could see in experiment, like drop in heat capacity, especially at lower temperatures, and what is observed, or what is the theory can predict. Today we are going to look at electrons, right? Electrons live in conductors. They can travel through conductors. They are responsible for, most remarkably, electrical current, and we're going to look a little bit at that today. But also they carry heat. So some of the leftover puzzles from heat capacity, we're going to also see how quantum theory of electrons in solids helps us address that. We are going to look at these two models today. One is actually classical still, just treats electrons as a gas, as a classical gas. And the other one, the Sommerfeld theory, is actually treating them as fermionic particles, and so introduces Fermi statistics, and so it is quantum. These theories both have success and still can be applied today, even the classical one, which is profoundly wrong. Some aspects of it are still useful. I use it in my lab to calculate practical things about semiconductors like mobilities. And Sommerfeld theory is even better than that, but they're both actually approximations. One dramatic thing they don't include is the crystal structure of materials. So the fact that these electrons we're going to talk about live in a lattice of nuclei that have their own charges, that interact with electrons, and that also impose periodic potentials, and what that does to the quantum mechanical wave functions of electrons is not treated today. We are going to learn that during the next spiral of this course, and we unravel more and more properties of solids. Okay, Drude theory is a kinetic theory of gases rewritten for electrons. And so it basically treats electrons as little balls that bounce around. And they bounce and they scatter off of things. Things could be nuclei like is plotted here, but they can also scatter off of each other. There's electron-electron scattering. Could scatter off of defects in lattices. Actually, they can even scatter off vibrations of lattices. So they can scatter off of phonons. So there are many, many things that electrons can scatter off, but doesn't matter for this theory because it doesn't go so deep as to consider these different kinds of scattering. It just says that there is an average scattering time averaged over all electrons. There is a mean time after which electron scatters. So obviously you can scatter faster than that, you can scatter longer than that, but actually the way the theory is written here is probability to scatter in time t will be 1. We'll see later. That makes maybe a small quantitative difference, but no qualitative difference. So scattering, that's assumption number 1. Assumption number 2 may seem a little weird to you, but if you think about it, it's still okay. So assumption number 2 is that after scattering, electron loses all momentum. So this must contradict some fundamental laws. Momentum conservation, for example, doesn't look like that applies here. But actually, if you look at one electron event scattering, that is certainly not correct. But if you average, then on average, you can say that momentum becomes 0. Okay. Now, as long as electrons don't scatter, they behave as just simply charged particles would in electromagnetism. They experience electromagnetic forces. So they experience an electric force and a magnetic force in between the scattering events. So external fields, we put this piece of conductor, this piece of solid, typically a metal, but maybe a semiconductor, into an electric field and a magnetic field, and they will just, the electrons will just deflect or accelerate or decelerate under the influence of that force. Okay, so let's go through these assumptions one by one to understand them a little bit better. Scattering time is a very, very useful concept which helps you both conceptualize what happens in complex systems with many, many things happening, and also to write down some numerical things about these systems. This is what is meant by scattering time here, is that the electron travels for time tau. After time tau, it encounters something and goes off in a different direction. Like I said, this can be impurities in a lattice. This can be other electrons. This can also be lattice vibrations. Can even be a photon if you're close to the surface where photons penetrate. And so the key word in this slide is that this is a phenomenological parameter, meaning that we cannot look at a piece of solid and just by knowing where the atoms are, how many impurities they are, what the density of electrons is, tell already right away what the scattering time is going to be. We can guess, but we cannot. There is no formula that would tell us what this time is supposed to be. So there is, we can, however, deduce this time from other measurements. Like we can measure conductivity, and we could, with some additional measurements, maybe with a whole measurement, deduce the scattering time. And I'll show you how we can do this as we go through Drude theory. Now, once we have gotten some kind of measure of this scattering time, we could later then guess, compare it to what we have in a solid, how many impurities, if we know how many we have, how many crystalline defects, which are probably scattering centers, how many, what is the likelihood of electron-electron scattering. And we could even learn about these things. For example, we could say, okay, it looks like this scattering time is dominated by impurities in this crystal. Right? So this is a very useful parameter for learning about solids, and Drude theory is the way to do it. It's perfectly fine even up to now, so it's not just a historical artifact that we're learning this. Okay, second assumption is about the one that sounds a little crazy, that after a scattering event, momentum goes to zero. Now, this is not so crazy when you consider averaging over all scattering events. So if you imagine a million of electrons that all start this way and go this way and then scatter in different directions, then on average, the average momentum after 1 million scattering events will be pretty close to zero. And so this is why this is not such a crazy assumption. If we assume something different, I believe it will not fundamentally change the result. This assumption, however, makes the calculation a lot easier. So we could account for all of these possibilities and then average over them later. But if we just assume this from the start, I will show you just on this board how you can derive the rest of Drude theory in just a few slides. Okay? So this, let's use this one, and even though it seems a little unphysical, it is actually all good. All right, and the last one is very natural. Between scattering events, you experience a force, and actually, in this lecture, we will see what happens if you have an electric force, if you have an electric field in the crystal, and if you have a magnetic field as well. So we will look at both of these scenarios, and in general you could have both of these fields present at the same time. All right, so let's derive Drude theory. Pretty much half of it is here and half of it is in the next slide. Okay, we go through the three assumptions and use them all. We're going to look at a time interval between t and t plus dt. So a very small time interval. And the rest of this formula can be understood from the following graph. In this time interval dt, there are two possibilities. Either electron will scatter, and the probability of that is dt divided by tau, which is the scattering time. So either electron will scatter with this probability, or it will not scatter and experience a force and the probability of that is 1 minus dt divided by tau. Okay? So for each electron, in a moment dt, there are these two possibilities. If we sum up over all electrons and take an average, then we have basically a sum of these two possibilities. Here, when it scatters, momentum goes to 0. When it doesn't scatter, momentum changes according to Newton's law. Okay, so this is exactly what is written here. So with the probability of dt by tau, we have momentum going to 0. And with the probability of 1 minus dt by tau, this happens to the momentum. dp dt changes under the influence of force. Or you can write it this way. This is the same thing. Okay, so then an averaged change in momentum during this interval dt is given by this. With a weight of 1 minus dt divided by t, momentum grows by f times dt. And with the probability of dt divided by tau, it goes to 0. So this term is just 0. If we expand these brackets, right, so we just have two brackets here. If we expand these brackets, we're going to have terms that are proportional to dt, and then higher order terms, like, for example, if you multiply f times dt with dt divided by tau, you'll have a term proportional to dt squared. That term is infinitesimally small compared to the other terms, so we ignore it. And so if we just leave these terms proportional to dt, we can write down this equation at the bottom in the red frame, which is the equation that tells us how average momentum changes as a function of time. Okay? So there is a term proportional to the force, and there is also this term that is basically tells you that there is a decay to some equilibrium state. Okay. So, for example, if you put the force to 0, then you will see that momentum decays to 0 after a characteristic time tau. And this is also very reasonable because with a small probability dt by tau, but the system loses momentum, there is a probability to scatter into a p equals 0 state. It's a very small probability, but as time goes by, more and more electrons will end up with p equal to 0. And so this is perhaps an artifact of this model that this current decays, but it is also true that the average momentum will go to 0 for a system of electrons once there are no forces acting on them. So even if there is some non-zero average momentum, after a time they will all, electrons will randomize their motion and momentum will go to 0. But in this model, they explicitly lose their momentum. They just becomes equal to 0. Okay. So here is this equation for momentum and what happens to it. And in fact, we know from experiments, and I'm sure you've done it many times, we know that if you apply a constant field to a conductor, then we get a constant current. Right? That's Ohm's law, or this is what happens when you hook up a battery to a resistor. You get a constant current, whereas here this equation features this term dp by dt, which means that electrons have a possibility to accelerate. Well, in fact, this does not happen, and so that's because there is a solution with dp dt equal to 0. So when dp dt equal to 0, this equation can still give us a solution, and this is the solution that the system takes. So this, when dp dt is equal to 0, a solution is called a steady state solution. So there is no time dependence to the parameter we're trying to find. So for now, it has been momentum. We will convert it into something more measurable in a bit. So a steady state solution to this, you just put this to 0. And this is now, we also plug in the electric field. We'll start by looking at what happens with the electric field. And so a steady state solution is just average momentum of this system is not 0. It is something, and this something is given by elementary charge times this phenomenological parameter tau that we cannot derive from microscopic details, but we just assume to be something, and times the electric field. So a constant force produces a steady momentum, finite momentum state on average for electrons. Now we can rewrite this equation in terms of current, which is something that we can actually measure. We don't really measure the momentum of electrons, we measure current. So the way you do that is you say P is equal to M times V, and the current density is equal to density of electrons times their velocity and times their charge. And so this allows us to express this equation in terms of current density J. And so current density J is proportional to the electric field, just like momentum is proportional to the electric field. This is average momentum. Don't put the brackets, but this is average momentum over all electrons. And there is this proportionality coefficient. Who remembers how this is called? When current density proportional to electric field, conductivity. Right, so this is conductivity. Right. And this is the same formula as you may have seen in another class, I think even Physics 2. And this is what comes out of Drude theory. Okay, simple enough, right? Equation of motion, look for steady state solution with a derivative going to 0, and find this solution in terms of conductivity. Now, conductivity is written out again here. What does conductivity depend on? We can see that it depends on the density, electron charge, electron mass. Okay, so if we had some other particles magically in a solid, these things would change. And this phenomenological parameter tau. Now, jumping a little bit ahead, I want to tell you how this formula could potentially be useful, start explaining it to you. Okay, so elementary charge of carriers in all kinds of conductors, metals, semiconductors is always E. That is the absolute value of it. Right? So at least the magnitude of charge is always E. There are some exceptions. Sometimes we're dealing with 2E charges, but then this entire theory doesn't apply. And sometimes we have charges, exotic things where charge is 1/3. But for most cases, that is always the case. So that's good. That's one solid part of this formula is this letter E. Pretty much everything else is variable, even the mass. Okay? So we will see that in a solid, mass can be heavier than the mass of an electron. You can imagine electron being slowed down by some other particles that attach to it, and so effectively becoming a heavier particle. You can think about this. Or it can be lighter. It can be 100 times lighter than the mass of an electron, the mass of a carrier in a solid. So this mass is quite variable. So you might be using the same formula for some semiconductor, but you will be plugging in a different mass here. You'll be plugging in a much lighter mass. And in that case, the mass is called the effective mass. In semiconductor, mass might be replaced by an effective mass, and that's denoted by m star. So we will see that hopefully later in the course where this comes from. I can tell you for now that it is beyond Drude theory and beyond Sommerfeld theory. So beyond what we talk about today, it comes from adding crystal structure into the model. Now, okay, but let's suppose this is just the electron mass, or you know the mass for this particular material. It doesn't really change from one chunk of material to the other. Then you can learn, in principle, by measuring conductivity, you can learn this parameter, right? It is in here. It is in this formula. So you could just extract it from the experiment. Except you also need to know the density. So if we had a way to measure the density of electrons, we could separate from just the conductivity measurement this parameter tau and learn about the mean scattering time or mean scattering length, which is sometimes called the mean free path. We could learn about how far electrons travel without scattering if we knew what the density was. And it turns out there is a different measurement we could do that will tell us the density. And it also can be demonstrated using the same Drude theory. But for this, we need to include magnetic fields. Okay? So now we look at the same Drude equation, which connects the average change in momentum with the applied force and the scattering process, scattering time. But now instead of the force, we plug in the full electromagnetic force acting upon an electron, which has the electric term, like before, also has a magnetic term. So this V cross B product is a Lorentz force. The Lorentz force is perpendicular to the direction of travel for the electron. Then the approach is very similar, but the outcoming math is a little bit more complex because of this magnetic field and especially because of this cross product. So we find a steady state solution. We put dp dt equal to 0, and this gives us this equation that connects, again, a steady state momentum to the scattering time and the force. And so we can rewrite, again, this equation in terms of not momentum, but in terms of current density. So using, again, the expression for current density, which has density of electrons times the charge times the average velocity of electrons, we can rewrite this expression in a steady state in terms of J. And so what we have here is, again, a relationship between E, the electric field on the left, and J on the right. But now this is a vector equation that is not so easy to make scalar, right? So if we try to write this equation in terms of something as simple as this, like we were able to do for this simple case without any magnetic field, we're going to have to conclude that this rho is a matrix, is a tensor. Right? And that's because of this J cross B product. Because of the J cross B product, rho must be a tensor. So the situation is a little more complex from the math point of view and also from the conceptual point of view. What does it mean that your resistivity is a tensor? Well, what it means in the 3 dimensions is that resistivity is described by this 3x3 matrix. And the 3x3 matrix has terms like rho xx, rho yy, rho zz, rho yx, rho xy, and so on and so forth. So there are different components to this resistivity. And if we just do the math, just stick with the math and then we will discuss what it means. If we just do the math and we take this equation and try to write it in terms of this matrix, and so we have to open up this cross product here, we will see that the matrix should look like this. Basically, rho xx, rho xy, so rho xx, rho yy, rho zz terms are all the same and coincide with what we found without any magnetic field, right? So these are just due to the electric field. This is the Drude formula, 1 divided by conductivity. So rho xx is equal to rho yy is equal to rho zz and is equal to 1 over sigma for B equal to 0. Magnetic field equal to 0. And then these terms that come due to the cross product with magnetic field are off diagonal. And they are terms rho xy and rho yx. Okay? And they are B divided by NE. And the other terms that involve Z are actually 0. And that's because Z is the direction of magnetic field itself. Okay. And this, the way this has been written out. All right. So this is the math. Okay, great. Now instead of one number for resistivity, we have a matrix. there seem to be two different values occupying this matrix. Well, 3 if you include 0. What does it mean? Well, it means that you can have Hall effect, right? Everybody remembers what Hall effect is? Yeah? Yeah, maybe? Okay. Well, Hall effect is very nice, and it can be explained in many different ways, but let's just stick to this matrix explanation, because these indices x, x, y, x, y, y can actually be related directly to an experimental setup that you use to measure them. So, for example, if I want to measure rho xx, it means that I'm going to apply electric field in the x direction and measure voltage in the x direction. So the sample becomes three-dimensional platform for plugging leads in different directions. So for example, if you look at the blue leads in the picture, they are hooked up in the x direction. And so I can source a current here, and I can measure voltage here, and this voltage will be Vx. And so I'm going to have Vx equal to rho xx times I x. So this would be a standard electrical measurement. Sometimes this is also called a local measurement. Now, what this local refers to is that you measure voltage along the same path as you measure current. So current, just electrical current that you're sending, is flowing in the x direction. You also measure voltage in the x direction. That's called local. Now, turns out what I can also do is I can send the current in the x direction. I can measure voltage in the y direction. So it's called VH here, but I'm going to call it VY. The board is not good enough for this, but Vy is going to be equal to rho xy times Ix. So I'm sending current in the x direction, same way as before. I'm measuring voltage in the y direction, and that voltage is not 0. And that's thanks to Hall effect, thanks to these off-diagonal terms in the resistivity matrix. Okay? And so this kind of measurement is called non-local. There are other versions of a non-local measurement, but this is one example of a non-local measurement where current is flowing along the x-axis, voltage is measured along the y-axis. Okay? So you can also convince yourself that Hall effect makes sense by thinking about what happens to an individual particle, like this electron here in the picture, traveling along the x. So his average trajectory is along the x, but he experiences a Lorentz force that deflects him to one side of the sample preferentially, and this is why there's a buildup of electrons on one side of the sample, right? This is how you could motivate Hall effect, but this is how you can do it from Drude theory in a very simple way, but you have to introduce this conductivity or resistivity matrix or tensor. Okay. Now, Hall effect has been measured extensively since the end of 19th century, and it's been measured for all kinds of materials. And what is convenient to compare is a Hall coefficient. A Hall coefficient just makes the measurement independent of the magnetic field that has been applied. So magnetic field is always in the z direction in the Hall measurement. But then if you introduce this rho h, the Hall coefficient, so it's rho yx or rho xy, those are the same, divided by b, then it becomes minus 1 divided by ne. Okay. Well, it's actually important to keep track of the sign of the Hall coefficient, and so I guess we should stick to the definition that it's rho yx divided by b, and then it has this minus sign here. But if we only cared about the magnitude of the coefficient, we could just take the absolute value, of course. Okay. So you can see why this is such a useful measurement. This coefficient is extremely useful because as long as you are sure that your particles carry charge E each, then it tells you the density. So remember I told you if we knew the density, then we could also calculate tau. And actually in the semiconductor physics, we often work with this mobility. Mobility is charge times tau divided by m. And so it's the same knowing tau and knowing mobility. Mobility is something that's you find more often in a paper or in a reference to a particular material. That's because when we quote mobility, then we don't need to worry about which tau we're talking about. Physicists, in the meantime, since Drude theory introduced 10 different versions of tau, which all mean roughly the same scattering time, but then maybe scattering time due to this, scattering time due to that mechanism. But mobility is very convenient. So we could figure out mobility by just measuring conductivity, but we need to know this density. So how do we know the density? We just measure Hall effect. We measure rho yx in addition to rho xx. So from a measurement of rho xx plus rho yx, two measurements, we could tell a lot, really a lot, about the material. And this is still used to this day to figure out mobilities and densities and so on. Okay. So this is just to say that this is not a useless thing, Drude theory. Now let's see how this theory does when applied to real materials. Let's have a look at this table here. What this table shows is Hall coefficients written in this form, which makes a couple of assumptions. So n that is here in this table is atomic density. So it assumes 1 electron per atom. So you can figure it out from a density of a particular material. You can figure out how many atoms per unit volume, and then you say, okay, let's calculate the number for the density, which will give us 1 electron per atom. And then in this form, 1 divided by RH over NE, if there is 1 electron per atom, then this column should give us, the middle column should give us exactly 1. Okay, is it clear? So if you look at this equation and move RH to the right side, you will have 1 equal to minus 1 over RH and E. Right. So if there's 1 electron per atom, we should have 1 here. How many electrons per atom does a material donate to be free electrons? Well, a good guess for that is the valence of these materials, right? The valence number of available electrons, electrons that can go to other atoms. So in a solid, valence should tell you how many free electrons you have, right? This would be a pretty good guess for that. And so for a number of materials, you have quite interesting results. For example, these ones here, lithium, potassium, sodium, are doing pretty good, right? The valence is 1, and the coefficient is the measured coefficient. That this is from the best measurements. It's pretty close to 1 as well. It's pretty close to 1. So you can say, okay, great, Drude theory applies pretty well to these materials. You can question why it is not exactly 1. That is maybe, at this level of simplicity for this model is not such a big deal. But then look at the other half of the table and you see some significant deviations. So for copper, deviation is already beyond what you might expect, because 1.5 is between 1 and 2. Same for calcium, same story, so it doesn't give a good quantitative agreement with this naive understanding, but especially this one, right, magnesium. First of all, it's tiny, 0.4, where we expect 2 for this column, and it has a minus sign, right? So even the sign is wrong, even though, how can this be wrong, right? So you have electrons going, and there is a magnetic field, they should all deflect this way, and so there should be a negative voltage, negative potential on this side of the sample, but this measurement suggests that it's vice versa. Right? So there is a big discrepancy right here, and this we cannot understand in Drude theory nor in Sommerfeld theory. We need to learn about the band theory of solids. But to not keep you tormented by this, in this material, charge carriers have a plus sign. So it's not that ions are moving, it's effective particles, which are called holes, are moving. Okay. So the wrong sign can be explained by the band theory. Okay. Questions about Drude theory? Anybody has questions? Very good. So, like I said, Drude theory has been successful and is still useful today. It is a very effective, simple theory. It gives a simple formula for calculating things like mobility, density, and especially for semiconductors. It is used a lot because each semiconductor, each particular crystal can have a different mobility, and it's very important to know it. To make further measurements with it. Semiconductors are very important for our IT industry, and so these mobilities are constantly being measured. Yeah?
What is finite frequency conductivity?
Well, so this is, like it says, we will not treat it here, but since you asked, I can say a couple of things. All of these theories get modified somewhat or quite a bit if you assume that the current is high frequency. So, or you apply AC voltage, or you radiate the sample with some kind of a microwave or terahertz or even optical radiation, and you can describe the response of the material to those types of excitations by conductivity as well. Like we described it now with a conductivity tensor to account for magnetic fields and electric fields, we can describe it by a frequency-dependent conductivity. Right? And what we derive now in the Drude theory is a zero frequency conductivity, meaning that we apply DC voltage and DC current. But you can learn many important things for high frequency conductivity. For example, there is another way you can learn about the density of carriers from measuring this conductivity and then extracting from it the so-called penetration depth, because these electromagnetic signals at high frequencies will not travel all the way through the material. They will get screened by charges moving together with these fields. So high-frequency response is a great area of solid-state physics, not to be covered here, but Drude theory even does well when you include finite frequency. Okay. Hall measurements can be derived from Drude theory and works pretty well for many materials, in particular for semiconductors. But of course, Drude theory is profoundly incorrect from the point of view of what electrons actually are, that they are quantum mechanical fermionic particles. And so the whole essence of it is profoundly wrong. And even though it gives correct formulas for many things, the foundations of it, the founding assumptions are incorrect. And actually, the easiest way to see that is not by thinking about conductivity like we did in the first half of class today, but to think about heat capacity again. So by the same parameter we were looking at last time. So it is especially apparent how it fails when you look at heat capacity. So we're going to build up to that. But if you remember last week, Tuesday, I told you that heat capacity is proportional to T cubed plus a linear term at low temperature. So it goes down to 0 as this power law. And we accounted pretty well for this cubic dependence thanks to phonons, right? Thanks to the Debye theory. And this linear term is what comes from electrons. However, if you keep thinking that electrons are just a gas of free particles and keep applying kinetic theory, then the thermodynamic side of that theory, not the kinetic or charge transport side like we talked about today, but the thermodynamic part will tell you that this is your heat capacity. And there is a large discrepancy between the measured beta and this one. Okay. So this brings us to Sommerfeld theory. Sommerfeld theory is a theory where, most importantly, we assume that electrons are fermions. And electrons being fermions means that there is only one electron per quantum state, right? And occupation of quantum states, the average occupation of quantum state, is given by this Fermi-Dirac distribution, which in a cartoon form depicted here, at 0 temperature, all the states below a certain energy level are completely occupied. This factor will give you 1. And they're completely empty above that level. So that level is mu, or the chemical potential. In this case, this is not mobility. This is chemical potential at 0 temperature. And this is a thing that is featured here in the Fermi-Dirac distribution. And we are going to also call that Fermi energy. So chemical potential at 0 temperature is the Fermi energy. And so the meaning of it is clear, right? Below Fermi energy, everything is occupied at 0 temperature. Above the Fermi energy, states are empty, completely empty. So this is quite different from being in an ideal gas from a classical point of view. And this is where the difference comes from. For simplicity here, let's treat a solid as a box, a three-dimensional box, which is filled with electrons. But now this is a three-dimensional quantum box. And we remember from our review that energy levels in a three-dimensional quantum box are given by this expression. So they are enumerated by these indices nx and y and z, which are numbers, and energy is proportional to the square of the number. And so once we have a bunch of fermions living in this box, then we are going to occupy these energy levels from lowest to highest. And so for the lowest level, all the numbers are going to get filled when all the n's are equal to 1 or 0. And then we will start increasing n higher and higher until we run out of fermions. Right? This is how this box, this 3D box, is going to be filled. So each of the wave functions for each of the electrons occupies the entire box. Right? Each electron lives in the entire box. But when we look in energy space, then we can put three x's here, nx, ny, and z. And in this space, we are going to occupy it from here, from the lowest point, and then we are going to occupy it around the lowest point. And as we go farther and farther from this 0 point, we're going to get higher and higher energy per this formula. Right? And so the final occupation at 0 temperature, at least, will look like 1/8 of a sphere in this space. Right? So this is n squared. So we will reach some energy where we have the maximum n squared because we don't have any more particles. Right? And so the radius, so if we just say, okay, all the states below some value E prime are occupied, then the radius of this sphere in the space of n will be given by this. This will be the radius of this sphere of occupied states. So all the states are outside with larger n in at least one of the directions are empty, and all the ones below are occupied. Okay. So, of course, it is extremely painful to work with these n numbers. What do they even mean in a real solid, right? This is really difficult to relate. I guess we can deduce them from the size of the box and so on, but it's much easier to just work with energy. Right? And in order to do that, you need to introduce, once again, the density of states. So the density of states is a function that tells you how many of these levels are in the interval of energy from E to delta E. And so you can see that this is a very important function because, okay, in the space of nx and y and z, the states are equidistant. They just occupy the sphere. But what if I want to plot energy versus the number of states? Or versus this, too close here, versus this function, right? Then you will see that there will be very few states here around low energy, and there will be a lot more states at higher energies. As we go out towards the surface of the sphere, all the states on the surface have the same energy. So there will be more and more states as we go out. So there is this very important function, which is the density of states. So more and more states at higher and higher energy. How can we find this density of states? Well, this is how we can find it. We can say that, well, if we integrate from 0 energy to some energy cutoff, if we integrate this function, we should get the correct total number of states. The total number of states here we can count by knowing how many n, how many fermions we have occupied. And so this total number of states is given by this volume of the sphere. So this formula is just 1/8, because we are 1/8 of a sphere. This is 1/8 times 4/3 pi r cube. That's all. So the number of states should match up. So from this equation, we can work out what this density of states is. So here it is again, the same equation from the last page. And of course, if we want to extract Fe out of it, we need to take a derivative of the right-hand side in E, right? So d right-hand side dE. Here we have e to the power of 3/2. Then the derivative will be proportional to e to the power of 1/2. So this is a very important function, which is called the density of states in a three-dimensional Fermi gas. Okay? Obviously, this answer will change if you go to 2 dimensions or 1 dimension, right? Because here we had to put the volume of a three-dimensional sphere in the space of nx and y and z. If we only have nx and ny, we have to put the area of a circle. Right? So there will be a different formula here. And so there will be a different dependence on E. Okay. So now what we learned is how many states at each energy we have in a Fermi gas. Now we can calculate what is the level to which this Fermi gas is occupied. Right? So in a 3D, we can talk about a Fermi sphere. All the states below that sphere, inside that sphere are occupied. All the states outside the sphere are empty. So this is the same formula for the density of states, but there is one more important prefactor here. We have to multiply the whole thing by 2 because now we are dealing with electrons. The previous one was more general, just for fermionic particles. Maybe they have 0 spin. Doesn't take into account that. But because there is a spin, 1/2, there is this thing called fermion doubling. So almost all things fermion are doubled just thanks to spin. Luckily, we don't have to redo the calculation. We can just multiply it by 2, and we get the correct result for electrons. Electrons in an empty box, right? This does not include any crystal structure and so on. Okay. So how do we calculate the Fermi energy? So the energy level to which the particles are occupied. Well, we just say that the number of particles in a given energy interval is given by the density of states times the Fermi-Dirac coefficient, right? Whether it's occupied or not. So at 0 temperature, 1 or 0. This is what this is, and times the size of this energy interval. And then the total number of particles will be given by integral of dn from 0 to infinity. So since we know the total number of particles, for example, we know the number of atoms, and each atom contributes 1 electron. So we know this number of particles. We can figure out from this integral what this mu should be to match these two up. Right? To get the right n, what should we put the mu at? So how big should be the sphere to have the right number of states? So it turns out if you take that integral in the limit of going to absolute 0, so infinite beta, it is very easy because the fermionic factor disappears. And you get this expression for mu or for the number of states. So you start with this integral, then you put beta to infinity, and so you have a Fermi filling factor like this. Here it's 1, and here it's 0, up to a certain energy, which coincidentally is mu. So that makes it easy to calculate mu. Okay, so now we are done with this counting of states. So this is slightly incorrect. You have 2 electrons per energy level. This is a one-dimensional picture. In 3D, there is a sphere. And so, like I said, this chemical potential at 0 temperature, which is the easiest one to calculate, we're going to call it Fermi energy. So how far the sphere is filled. And now come the interesting part. People have done this calculation for various materials, and so the simplest one you can imagine, copper, just a metal, really good metal. Do it for copper, and you can calculate what the Fermi energy is in copper. Turns out it's 7 electron volts. Now, is it large or small? Well, one nice thing I like to do is to convert energy into temperature. You just divide it by K Boltzmann. Turns out that temperature is 80,000 Kelvin. If you just calculate it this simple way, if you just define Fermi temperature as Fermi energy divided by K. Right? So electrons at the top, so all the states up to 80,000 Kelvin are occupied. And the states above 80,000 Kelvin are empty. So you can say you're at room temperature at 300 Kelvin. We are occupied up to 80,000 Kelvin. So this approximation that all the states are empty and all the states above are occupied is largely very, very true for copper. Right? You can also define Fermi momentum by saying that Fermi energy is equal to P Fermi squared divided by 2m, and you can define Fermi velocity from this Fermi momentum. So given this energy, you can define Fermi temperature, Fermi momentum, Fermi velocity. Now, what would be the Fermi velocity that corresponds to this? I believe it's something like 10 to the 6 meters per second. So electrons at the Fermi level, at the top of that occupied sphere, are cruising at 1 million meters per second speed. Right? So this is very, very different from what Drude theory would imagine, right? Certainly, when these electrons scatter, they don't go into the zero momentum state, right? They are at 1 million meters per second. That's relativistic already. Right? So this is what comes from introducing this Fermi-Dirac statistics. All the states here at the bottom are filled up to velocities of 1 million per second. Now, this has some implications further. Like I promised, we're going to look at what happens with thermal transport. Okay, you can also conveniently rewrite the density of states in terms of the Fermi energy, and it is a more elegant formula. But still, density of states is proportional to energy to the power of 1/2 in 3D. So this is in 3D. Okay. Back to heat capacity. Here an important consideration is that in order to be able to absorb heat, electrons should have states to go to with that extra energy. So this is what I mean. Let's imagine this is the Fermi sphere, right? So this is some three-dimensional state of n or k, some kind of three-dimensional space. And the point is, if you are stuck here in the center of the sphere and you want to go outside the sphere, you need to cross this distance radius r, and you remember that radius r is an energy. That's the Fermi energy, and that is 80,000 Kelvin. Right? So what that means is all these occupied states here in the middle of the sphere are not going anywhere. There is nowhere for them to go. All the states around them are completely filled. All the states are completely filled, and if I give them energy of k Boltzmann T, which is what I have, that's the only thing I can give them at the temperature T, even at room temperature, I don't have enough energy to kick them out of here, out of the middle, to the outside of the sphere where the states are unoccupied, right? So inside the sphere, this fermionic statistics, the Pauli principle that tells you there can be only one particle per state, or if you account spin, 2 particles per orbital degrees of freedom, prevents me from using any of these electrons inside for any kind of absorbing energy. Right? They have just simply nowhere to go with that extra energy. So the only electrons that are relevant are living in a narrow interval next to the Fermi energy, pretty much kT to the left, kT to the right. Those electrons, and only that thin sliver of electrons has enough, can absorb kT and go to an empty state. And so this is also kind of the reason why Fermi distribution smears out. So some of the guys here at finite temperature decide to jump over there by absorbing an energy of order kBT, and so it becomes a bit blurred in this region. But if this energy is 80,000 Kelvin from 0 to the Fermi energy, and this interval is about 300 Kelvin. So it's more than 1,000 times smaller. And so that means that largely Fermi gas is useless for heat capacity purposes, and the only electrons that are relevant are here. This leads us to this consideration here. So the number of electrons that are living in this range are the density of states times the energy interval. That will tell us how many are there. And how much energy can each of them absorb or release? That's kT. Right? So then energy of a Fermi gas as a function of temperature is some constant. This is E0, means this is temperature independent. Largely this is just counting all of these occupied states here, which nothing happens to them no matter what temperature, plus a small correction, some coefficient, which is not known to us as of yet. We are actually not going to explicitly calculate it, times the number of electrons in this range, times the energy that they can absorb. And obviously, as we increase temperature, this window grows. More and more electrons can participate in this taking and giving of energy, and the heat capacity increases. Okay, so then the heat capacity is d dt. So we take this expression. It is proportional to k squared, t squared, also k squared. And so heat capacity will be proportional to T. And if you plug in the correct gamma, which you can calculate, it's not so difficult actually, but we're not going to do it here, you get this expression for heat capacity. Now this correctly predicts that heat capacity is proportional to T. If you remember, that was the outstanding puzzle that we didn't resolve from heat capacity measurements as a function of temperature. And so now we know that this linear term, this T term, this comes from the electron subsystem living in a solid. Cubic term comes from phonons. Linear term comes from electrons. Okay? Now, let me point out one more fantastic, actually, this is a really amazing thing that happened to physicists. Doesn't happen very often. Basically, a mistake was made twice, and the result was correct. So this is a very, very nice example that is really worth going through. And in the last few minutes, I think I'll be able to squeeze that in. For this, we need to recall what is this kappa, which is thermal conductivity, right? So this talks about carrying heat. Electrons that move through solid carry electrical current because they're charged, but because they have energy, they can carry heat. So if one side is hotter than the other side, there will be some thermal transport happening. And so this is described by this formula. Q is thermal current, not electrical current, and it's proportional to temperature gradient, and the proportionality coefficient is this kappa. So this is an analog of resistivity, but for heat. Okay? And there is an intimate relation between the two phenomena because it's carried by the same particles. But without going into too deep into this, formula for this heat resistivity is also actually pretty similar to electrical resistivity. It has tau. This is the same tau from Drude theory. It has density, but because this is heat, it also has heat capacity. And it has the average velocity. Okay. So lambda is here is a mean free path. This is when you take average velocity times tau. Okay, so let's first apply classical kinetic theory of gases and try to work out what this kappa is. So classical theory tells you that, well, the average energy per particle is just given by temperature, right? We already know that this is completely not true. This average velocity is the Fermi velocity. And so this energy is a Fermi energy. But, okay, because this is the classical theory, this is just 3kT. And so if we plug this in to the expression above, we get this expression for thermal conductivity, which has temperature, density, tau, all the other things that are related to just electrons bouncing in a solid. So the principal mistake is here. Right? So this is obviously wrong, but we apply it any case. And then people have noticed from measurements is that if you measure thermal conductivity and electrical conductivity for the same material, there is a relation between them. And that is called Wiedemann-Franz law. This is a sort of an empirical law. So many, many materials measured. The same thing was found that if you take a ratio of thermal conductivity and electrical conductivity sigma, then you get a constant times temperature. So if you take kappa divided by T sigma, you get a constant. And this constant is very similar for many, many materials. Okay. Turns out, if you take Drude theory that is based on classical theory, you have to take this expression, you combine them, and works out that this indeed is a constant and is a fundamental constant, which is the Boltzmann K, electric charge, and some prefactor, nothing else. So, if Drude theory is wrong, if this formula is completely wrong, and we put the wrong energy in here, why did this work so well? So obviously, if you look at this here, velocity that comes into this expression, this v squared, has to be much, much higher. So there is something that is really wrong here. Well, here is the reason. So like I told you, mistake was made twice. Now, in Sommerfeld theory, we have to take a different v squared. And so that v squared, so we take heat capacity from the Sommerfeld theory, which is this one. And so now, instead of being 3/2 kT, there is this T divided by TF term. However, v squared, which we also have to put in here, is proportional to TF. So here we have TF in denominator and TF in the numerator. And those two TF cancel out. And so by coincidence, this Wiedemann-Franz law still works similar in Sommerfeld theory and in Drude theory. However, it is a pure coincidence. Mistake was made twice in the Drude theory and got the correct result. But for a while, this was considered one of the best confirmations of Drude theory. It turns out it's completely incorrect. However, you can still use Wiedemann-Franz law if you want to, because it is accurate. And the formula is pretty much the same. Okay, so the physics of this is that you have, of course, much higher energies involved in electrons at the Fermi level, but you have much fewer of those electrons, because most of the electrons in solid don't participate in this transport of heat. Only a thin sliver participates. And so even though each of those electrons has much higher energy, there is much fewer of them, and this works out, for example, in this formula. Okay, I think we have to stop at this point.